In the AI era, speed to capability has become the ultimate competitive differentiator. The ability to deploy infrastructure in a matter of months rather than years is no longer a luxury, it's the requirement. So for us today, we've got Ivan joining us, Ivan Dragonik, a senior solutions architect at Vertiv. And Ivan is going to explore exactly what prefabricated infrastructure means for AI deployments, identifying where it fits, and just as importantly, where it doesn't fit.
Thank you for the introduction. Okay, thank you. I'm going to share the screen right now. Just give me one moment. Okay, so first of all, thanks for the introduction. Thank you for the opportunity to be here in the first place. So, like Julio said, this session, we're going to focus on how data center industry is adapting to the AI workloads, to all the GPUs, all the generative AI, all the hyperscaler demand, all the AI that we've been hearing about for the past several years, and specifically on how prefabricated infrastructure is dealing with all of that and how we're dealing with those challenges. So to start off, what's the deal with liquid-cooled data centers and with AI? So first of all, most of AI chips is liquid-cooled. If we talk about NVIDIA, we know there's the GB200 chip, which is now kind of the old story. No one really does it anymore. So now we have GB200 had like 80% of the cooling load liquid cooled. We have the Vera Rubin chips now, which are approximately 87% liquid cooled. So we're still seeing a portion of the air cooled loads here, but most of the stuff is liquid cooled. The reason driving that is just that the chips, the density of the GPUs is getting higher and higher. They have developed technology where they can just stack more and more silicon on top of each other. Really, as a mechanical engineer, for me, it's that simple. There's more power in the same place, so we need to cool it down. The only way to do it is liquid cooling. With the liquid cooling, we're also seeing a minimization of footprint. And by minimization, I mean what used to be a 500 square meter data center, maybe there was a 1 megawatt of IT load in there. Now we see that load in just one aisle. So we have a massive reduction in footprint per megawatt of installed load. Maybe one of the big questions is where we're seeing all these applications for data centers, for AI precisely. So everyone talks about artificial intelligence and generative AI. Everyone, it's like you just open a bottle and Gen AI pops out every day. But that's not all AI is about. Yes, the big hype is about generative AI, about ChatGPT, and about all of that. But traditional AI is also being used more and more. And we're seeing it across all the industries. We're seeing it in factories, in healthcare, in finance. We're seeing it basically everywhere around all the industries. The generative AI is the biggest portion of everything here. And the reason for that is the hyperscalers and the big collocator companies that are now building more and more for the AI. So when you see memes on the internet saying we need more data centers for AI, it is mostly generative AI, training models, and hyperscalers, big companies like OpenAI with Microsoft and Google, Meta, all of these guys. But how do these AI data centers change the environment? How do they have different requirements? So first of all, there's only limited space. Adrian was also talking about power. There's limitations of power across Europe. We know that the big hubs like Dublin is practically at a full stop right now. Frankfurt, Amsterdam, all of these big data center cities don't really have a lot of power available anymore. So that's one of the key requirements that we need for a big data center. We need a lot of power, for AI especially. The cable lengths need to be maintained, equipment needs to be at certain distances, for example, up to 150 meters for Ethernet. There are ways of doing fiber connections a bit longer than that, but still there are limitations in many ways. And transition to liquid cooling is definitely something that is the biggest challenge that I would stress out in the today's world of data centers. The liquid cooling is the topic to discuss. So just to focus a little bit more on the markets, I've mentioned high performance computing. So high performance computing is not AI. It's something that has been around for many years, and liquid cooling has been around for many years. By many years, I mean like up to 10 years for high performance computing. And a lot of companies are using it for research. For example, oil companies are doing some detailed oil rigs calculations using HPC. But when we start talking about AI and generative AI, for example, we have a lot of companies using it for their own purposes. I'm just going to stress out once more, the colocation cloud providers and the hyperscalers, these are the guys that are using the most power and that have basically installed most of the AI solutions that we see today. All the Gen AI models that everybody is using from day to day for like changing somebody's appearance on an image or just writing text that you're lazy to do. Most of that is based on hyperscalers like Microsoft, that OpenAI, that has built these massive data centers based on NVIDIA, mostly GB200 and older like B200 chips, strictly air cooled. So maybe an interesting point to make that most of the AI stuff that we are now using in our day-to-day life are models that have been trained on traditional air-cooled GPUs, graphical processing units. So the new GPUs that are coming right now are just so much more powerful, and their power to token and just basically cost token is significantly lower. And so we can only imagine the power of the models that we are going to see in the next couple of years. I wanted to mention finance and government, media, entertainment. These are types of clients that do use AI for their own purposes. There's numerous applications like chatbots and all of the stuff, but the massive surge is in the hyperscalers and collocators, like basically like it was before AI. So the capacity is surging. The power availability is lower and lower. What Adrian mentioned before, we're seeing a lot of capacity going to Nordics, and that's a good thing. Basically, the Nordics is a cold environment. They have the power availability. They have what's called green energy, and it is in fact green because they use a lot of wind and a lot of solar. But they have the power. That's the important point. They have the available power, and which is why in the last year or so we are seeing more and more switch of large deployments going to the Nordics. And the cooling architecture is switching more and more to the liquid. I mentioned before we have like 80%, 90% of total GPU load at liquid cooling right now. It is going to change. Basically, the only thing that's still being air cooled in the modern GPU is the power source, the DC inverters. The thing that we will see happening in the next 2 years is the DC transformation to DC power. So basically, the Vera Rubin chip from NVIDIA will have a sidecar, which will be distributing the 800 volts direct current directly to the AI chip. So there will no longer be DC inverters installed into the rack. At that point, we will have most likely 100% liquid cooled architecture. But maybe just to keep in mind, when we say 100%, we don't really mean 100%. There will always be a little bit more that's just transmitted to the environment. There will always be like a percentage or two that's left for the traditional air cooling, but we like to say 100% because that sounds so clean and so modern. Okay, so what's the deal with prefabrication, and how does prefabrication help scaling at speed? So the challenges is also been mentioned before in the introduction. The speed to market is changing. Everybody is buying these very, very expensive GPUs, and they want their tokens being produced immediately. Literally, we're talking millions of dollars, euros every day if these GPUs are not utilized. So a 50 megawatt data center 5 or 10 years ago would take probably 3 to 4 years to complete in its entirety, and now we're talking more in months, where we're saying everybody is wanting to have a deployment speeds that are just unprecedented and just something we haven't seen before at all. So the liquid cooling and the power density is changing, and we're trying to build all of that, trying to put all of that into prefabrication. What used to be megawatts is now gigawatts. This is very important to mention. So the scale, and I've mentioned this before, the scale is just bigger because the density is so much bigger. We used to have racks that were like 5 kilowatts per rack and were maybe up to 10 kilowatts per rack. When we mentioned 20 kilowatts per rack 10 years ago, that was very, very high density, and we needed rear door coolers, and we thought that we cannot even cool it with traditional perimeter air cooling. As it turns out, we can actually cool a lot more with traditional air cooling. We just need a lot of air conditioning units on the side. So right now, if you take a typical Vera Rubin rack from NVIDIA, and we know that it's approximately 200 kilowatts, but there's still like maybe 30 kilowatts or more that's traditionally air cooled on the air cooling side. So it's just become the new normal. So the solution that prefabrication is actually offering is to compress the schedule by prefabricating in the factories. So the thing that we can do is we can do the parallel approach to on-site building and critical infrastructure manufacturing. So while the site is being built, we have the slab preparations, we have all the underground conduits, ducts, we have the medium voltage rings being built out. During that time, we can build the critical infrastructure in factories so that when we come to site, there's basically 80% of the work is already done. When compared to traditional build out, when you would have your slab done, and then you will start building the walls and all that, and the concrete needs to dry out, and it will take a lot more time. The second big point is the reduce of labor and reducing the integration risk on site. Obviously, with the prefabricated solution, we will need a lot less labor, and especially a lot less of the highly skilled, qualified labor workers on site. And the reason is because everything was built in factory, and the factory has already pre-tested, done point-to-point tests for BMS, commissioned the data center basically up to level 3, and then level 4, level 5, we will still have to do it on site. But overall, it will take a lot less time, and the labor required will just be significantly reduced. The quality of design is much better. So when something is being built at factory, it is on the floor level. We're building it with precision and with skilled workers. When compared to site work, which is always on ladders, somewhere high above, near the ceiling where the bus bars go, somebody's trying to install a type-of box. It's just that the quality of the build is better when we do it in factory. And the commissioning outcomes are better too, because we simply have, like I mentioned before, pre-commissioned and tested these things before they come to site. Okay. So how do we approach the gigawatt scale? So what, like 10 years ago, even 5 or 6 years ago, a 50 megawatt, a 10 megawatt, a 100 megawatt data center was a huge hyperscale data center. Nowadays, 50 megawatts is below the radar. Everybody is talking gigawatts, and I can tell you, if I had a €1 for every time somebody said they were building a gigawatt data center in the past year and a half, I would probably have like at least €25. I don't know. So, and that's just for the EMEA. I don't even want to mention the US, where they're just building multiple gigawatts and trying, like one of the colleagues said, it's just bragawatts. It's who's building more. But the thing about that is, it still needs to be built. And so how do we build it with traditional approach? We do the repeatable blocks design. If you look at the image on the right, the top picture is the 250 megawatt data center, AI GPU filled data center. So it will feature several data halls. There are like 4 distinct data halls on the right hand side and 4 data halls on the left side. In the middle, we have a core networking section, which is a prerequisite for such a big data center. It is where all the networking combines and where it just gets routed to be able to go outside. If you look at the 125 megawatt reference design, it's basically half of what we had above. So we have just, for the big one, we've just copy pasted this. And then as we go lower and lower, we go into more and more repeatable blocks. And then on the next slide, I'm going to show you how exactly one of these blocks is actually built and what it consists of. But just before we go into that, I would just like to focus on this scale here. I think maybe one very, very interesting thing to note is the scale of the cooling infrastructure on these sites. The whole white portion of the image is the chiller yard. And even with very, very efficient chillers and with liquid temperatures that utilize practically free cooling all year long, we still have half of the site that we need just for the cooling infrastructure. And the reason for that is the thing that I mentioned before, the density. We used to have 2 chillers for a 500 or 1,000 square meter data hall. And now for a 500 square meter data hall, we probably need 10 or 15 chillers. So that's just the way it scales. So the chiller infrastructure is becoming the main footprint driver. Well, the power as well, obviously, but it's not so blown out of proportion, I would say. So, okay, a typical modular program. We call this the one core. And the one core is it's a reference design. It's a platform. It's something that can be repeated on the inside for the white space, as well on the outside for the power infrastructure and the cooling infrastructure. So I'm just going to go through one by one and quickly describe the elements that we have here. The white space is filled with what we call smart run, and the smart run is a prefabricated infrastructure that houses the critical power for the GPUs and for the other IT equipment, and the cooling, liquid cooling secondary fluid network infrastructure as well. So it's being built on steel skids that are either self-supported, mounted on the floor, or can be mounted from the ceiling. Can be a combination of both if needed. And on those steel construction, we install the critical infrastructure. And the thing is, it's already prepared for the NVIDIA requirements, sort of like the distributed redundant topology with the bus bars for the 4 to make 3, and then the liquid cooling topology with all the branch offs and all the things that need to be for the liquid cooling system to properly operate. We also integrate the control cables and control systems, and liquid detection system. So if anything leaks, there will be trays for liquid, and there will be liquid detectors that will alert the BMS operator of a leakage. And it's also funny, like traditionally we never wanted to see water above racks. That's, oh no, you don't go with water above racks. Well, now we have water inside the racks and it's completely normal, but we're still very worried about liquid leakages. But it's still something to take care of, and now more than ever it's critical because there's a lot of fluids, and there are special schemes and ways how to deal with that. So that's the inside. We have the smart run, that's a modular infrastructure being brought into the white space. On the outside, we have the power modules. This is number one. The power module is a combination of medium and low voltage power. It features a medium voltage ring main unit for the medium voltage distribution topology, the transformer from medium voltage to low voltage. And then on the low voltage side, we have the low voltage distribution panels, which feed the UPS. And from the UPS, we have the outgoing bus that feeds all the critical infrastructure in the white space and the cooling equipment as well. It also there we have the batteries inside, we have the appropriate cooling, and we have all the BMS systems. So the power module comes to site as a single structure, self-standing structure, that is weatherproof and able to power the critical infrastructure. We also have some of the cooling corridors on the outside and the cooling modules, which are basically used to reticulate the bus bars, so the power and the cooling all around the data center. These data centers feature concurrently maintainable power and cooling topologies, and that's all installed on these kits that go around. Number 6 is the heat rejection skid. So it's basically a continuous cooling tank that's coupled with a trim cooler or a traditional air-cooled chiller. So the trim coolers is something we use exclusively for the GPU cooling loads mostly, because the GPUs nowadays can take the temperatures up to even 45 degrees. So which means the trim cooler is basically a dry cooler that will operate in dry cooling mode most of the year, but it also has the compressor installed, so it can ramp up the compressor and it can take care of the peak loads during the summer. If you just have 1 or 2 days in summer when the temperature gets above, I don't know, 35 degrees, that's when the trim cooler activates the compressor and we still have the cooling capacity that we need. And the key point is without water usage. These systems use 0 water, and that's also a very interesting topic to discuss. Also, as Adrian mentioned before, some of our clients ask still, like, but you didn't provide the water usage. We told you we need the water usage for the data center. You didn't give us anything. And guys, I told you it's 0. We only use the water for flushing the toilets in your office space and maybe for drinking. That's it. Humidification of the air inside. These systems use 0 water, and that's great, especially in the Nordics where it's sufficiently cold outside during the entire year that you really do not have to use water. And with the trim cooler, we can only use the compressors for certain small amounts of time during the peak summer. The continuous cooling vessels are mounted on skids, and they come equipped with valves. And these valves have a controller, and the pump inside the chiller and the valves are controlled by the chiller. So the great thing about prefabrication is it's all pre-programmed, pre-installed, tested, prefabricated. So these chillers will control the valves and they will know how to operate the system given the certain cooling modes. They come up with up to 8 pre-programmed chill water operation modes. So there is no fuss on site. There is no commissioning engineers running around trying to set the valve flow properly. It's all tested in factory and done. So there are some more items. There are like hydro modules, which are also prefabricated structures. We put them next to the building, and these are your engineering rooms for the chill water systems, for the filtration, water softening, and chemical dosing and systems like that, pressure maintenance systems that are critical for operation of any chill water system. So this is the system that we would scale up. And I'm just going to go back one slide. On the lowest image, this is the system that we were looking at. We start scaling it up. We start copying and pasting. The arrangement changes, but basically the main idea is the same. We can scale this up to gigawatts. So where we have our R&D guys working on a gigawatt reference design, which is basically this, very similar to this, but copy pasted 4 times. Okay, so last but not the least, the Vertiv Unified. This is a control and automation system that covers all the systems that I've been mentioning on the previous slide. So power infrastructure in a data center needs a lot of metering and controls. The thermal needs a lot of controls. The IT solutions need even more. Even the facilities, if you have your office spaces, and the office spaces will still have air handling units and fire dampers and stuff, will still need the control. So the Vertiv Unify is a unified system, hence the name, which controls all the critical systems and the non-critical systems in the data centers. From field level, where the monitoring equipment like power meters on every type of boxes, and we're talking hundreds and hundreds and thousands of power meters, to power meters inside the switchgear for monitoring the UPS outgoing switches, the incoming breakers from the generators, from the utility. Everything is being monitored and displayed on a central Unify SCADA, which we also provide. So the thermal systems, I've mentioned the liquid cooling system and the valves that we have on there. All the systems are monitored. We have the control, and we can stop the leakage based on the leak detection system. We know where the leakage is happening, and we have automated solenoid valves that can, at operator choice, just snap a finger and stop the flow through that branch. So I think I'm almost out of time. Julia, is that am I? Yeah. So
Apologies, yeah, we're just running it slightly over.
Okay, so I'll just stop here, and
No worries.
I'll just kindly ask if there are any questions. I would be happy to provide answers.
Yeah, 100%. I can already see we've got some questions in the chat. So I'm going to ask the first one I read is, so you've advocated for standardized repeatable blocks over the tailor-made one-offs to achieve speed. Does standardization mean operators have to compromise on their site-specific requirements, or is there still room for the customization elements?
Yeah, standardization is great, but there is always customization. I'm not gonna lie, every project is different, but some of the elements can be repeated. Like the power distribution is very typical for your state-of-the-art GPU architecture. For example, all the GPUs nowadays use 4 to make 3 power architecture. So that's something we can install in the smart run, and we can just use across multiple data centers. And then the smart run is typical. The power distribution, the power module is standardized, but there will be customization, especially if needed. Any customization does slow things down. So if speed is the primarily requirement, then I would suggest just go with the standard and find a way.
Of course.
That'll be short.
We've got one more question. One more question just to keep track of time. So, final question I'll ask is: so you've shown the prefab options, and you've reduced deployment schedules by 20 to 50%. Outside of just saving time, at what megawatt scale does the prefab move from being the fastest option to the most cost-effective financial option?
Well, that's a very good question. That's $1 million question.
Yeah,
and that's a question I've been asked 1 million times. Look, it's very difficult to answer. It depends. Yes, it depends.
True.
So on the large scale, it will definitely provide speed. On small scale, maybe not. On a smaller scale, you could be just fit out the white space. Traditionally, you could probably gain more traction and do it faster. So it's difficult to say. I would say the sweet spot for prefabricated elements as such starts at 5 ish megawatts, and
Okay.
then expands on. Anything below 5 megawatts, it's discussable. Anything below a megawatt, probably just fit it out yourself. But
Makes life
there's no
easier.
rules.
Of course, makes sense. Sorry guys, we're gonna be a little bit behind times. Any more questions, we're gonna answer it down the line. We'll send out a publication, so not to worry. Ivan, thank you so much for your time. I really appreciate it.
Thank you very much. Pleasure.
Thank you so much.